All right, good morning. How are you? Doing okay? Good. Um, I didn't quite get to the grading the homeworks. I've done the MATLAB assignments, so I'll get you some feedback. I haven't posted it yet, but I'll put that on Moodle pretty soon, along with the homeworks and their grades. And also by next class, I plan to get you the next homework assignment. So that'll give you about 2 weeks, I think, to do that, and that'll kind of constitute our next segment of the class. I'm considering trying to cover redox chemistry and just go a little lighter on carbonate stuff since we already covered that. So I might adjust the syllabus again, topic-wise, for that kind of stuff, but I'll let you know as I get there. So today I wanted to come back, kind of finish off the complexation reactions, equilibria stuff, show a couple of examples of what those look like in practice, and then move on to solubility. Now, as we'll see, a lot of what we've done so far has already touched on the fundamentals we need for solubility, so it's not adding too much new in its own right, like how do we approach a problem necessarily, but we will get to a point where we can look at or develop visualizations that are quite helpful to see, okay, at what pH and concentration range do we expect something to be coming out of solution as a solid or being dissolved, for example. Okay, so solving the complexation systems. Now, we talked about it briefly, and I think maybe I'll shut the door because I'm getting distracted at least. Chatter. One moment. All right. So I think we've talked a little bit about it, but we can solve our complexation problems. We talked last time about each hydration, each water coming off and allowing something like chloride or some other ligand to attach to a metal. That can be a sequential equilibrium system. So then we end up with lots of equilibrium equations. And in the example we looked at, 8 different species, the complex with water, with multiple waters, the complex with, in that case, I think we were looking at ammonia or with chloride. So we can calculate lots of different versions or species of a given metal complex with the ion or with a ligand. And that's just for one particular metal. But if then we change the oxidation state, that sends a whole new sequence of complexes to consider. So there's quite many species. All of the stuff we've learned so far can be applied. All the equilibrium principles we did with acid-base stuff, that could be used. So we could do algebraic, or we could do a graphical approach. But typically it's just not practical because the systems are too complicated. So we have sometimes competing acid-base chemistry, sometimes the solubility itself, that we're going to cover a little more of, can start to come into play. So in most cases, it gets kind of too complicated to deal with. But I did want to look at one of the simpler cases. So if we take a trace metal, sometimes those are a little more manageable because we can say that they're probably not going to be at concentrations that would affect chloride, for example, the ligand concentration. So if we take lead in seawater, complexing with chloride, it's a pretty good example because with just that, we might be able to take a graphical or algebraic approach like we had with some of the other systems. So if we make a couple assumptions, first of all, the trace metal's low enough concentration, trace, so that it's not really impacting the concentration of anything else. We also can typically assume that we can ignore any activity coefficients in that scenario. And then also assume that there's no complexation by dissolved organics or some other organic molecules around. Maybe that's can be reasonable for some cases as well. So, going to walk through some of how the book shows a hypothetical student tackling this kind of a problem. So we have lead 2 in seawater. So lead exists in natural waters as lead 2. Total concentration in the surface layers of the world's ocean is approximately 14 nanograms per kilogram. That's 14 nanograms per liter, or if we change that to molar, 7 times 10 to the minus 11th moles per liter. So we've got Liam. He's a new grad student, and he only knows a little bit of chemistry, but apparently he's a go-getter. So he's told by his advisor to calculate the lead speciation in seawater. He's also told that it's dominated by chloride, because the concentration of chloride is quite high in the ocean, about half a mole per liter. So Liam proceeds to calculate the fraction of lead 2 complex with chloride in seawater, and initially finds a stability constant for the complex with a log K of 1.56. And what he's looked at is Pb2 plus Cl minus goes to PbCl plus. Okay, so that's his initial venture. So unfortunately, he was wrong, because that's not the only thing. He was erroneously thinking that was the only species he had to consider. And so he calculated the distribution between those two as follows, which, maybe is a decent first step to say, okay, well, here's one, let's check that one. Okay, so he corrected the stability constant, the concentration-based constant, by computing activity coefficients using the Davies equation. We mentioned that, and probably, I guess in seawater, the activity might be important, but if it was just a lead by itself, yeah, that wouldn't, that's what I was talking about. If it was lead by itself, we wouldn't really have to do any correction. But he did all this correction, which is great, and got those factors and calculated a log K, the corrected one. That's a 0.922. And then he proceeded to solve the problem, meaning what he's trying to do is solve for, okay, how much is there in one form versus the other. A lot of times when we're saying let's solve the system, maybe we're trying to identify the pH of that system. A lot of times we're solving to find the relevant species, right, and to calculate each of those. Okay, so then he takes the equilibrium constant, sets it equal to the products over the reactants, and finds the portions that are in each form. So in this case, there's 4.559 times as much of one, I guess, PbCl plus as there is Pb2 plus. Okay, so he solved that solution. And then he wrote out the mass balance for the problem so he could put in the numbers and find a total. So he found those values. And then based on those calculations, he concluded that 82% of lead in seawater, the lead 2 plus, exists as that monochloro complex. Now he showed these results to his advisor, so this is leads into the next example. And he learned that, oh, well, you can have more than just one Cl complex, right? So it can be multiple ligands attached. And so he's told to do a little more research about these other complexes. And so he goes on and finds, all right, well, now we have 4 versions of the chloride. And he goes on and does more mass balance and blah, 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 blah. So he continues. Okay. He puts all that together and he says, oh, okay, only about half, 48% of the stuff exists as that monochloro complex. And then he checked his calculations. He added all the concentrations he got, he got a value for each one, added them all together, which should come back to the total. And sure enough, his total was fine. So he's like, okay, that's pretty close to the commonly reported thing. So, okay, that looks pretty good. So he brings that back. And then this grouchy old professor says, nope, try again. There's other stuff. So he goes back to it. And this time, the problem says he goes to that visual MinTech program that I've mentioned before, we'll talk a little more about today, and says, well, there might also be bromide and carbonate and bicarbonate, fluoride, sulfate complexes. Okay, so he goes and does a bunch more work, and I'm just kind of skipping ahead a little bit. And so with all of that, we have a table I'll show you, I think. You can get 19 different complexes for the lead and seawater. So what we started with as hoping to be something we could just do algebraically, maybe just put a little graph, turns out to be a little more complex if you're considering all these pieces. Now, not all of those 19 were relevant in terms of concentration, maybe had no real impact, but to know that, maybe you have to solve each one of them, right? So at that point, the manual calculation approach, just even for this simple case of lead and seawater, is not maybe so simple. Okay. Now, maybe if we just had a little bit of lead in a relatively dilute solution that is also rather pure, like meaning it doesn't have all these different species of potential ligands, maybe that's the time we could do it. So here's the table, the 19 different species, and we could take a look at the net concentration for any one of them. We can also take a look at the log beta. These are the cumulative constants that we talked about last time. So if we take a look, when they're up at 10 to the minus 11, that's pretty small compared to 10 to the minus 7. So those are probably not too relevant. We look down, a lot of these are not so relevant. And then, let's see, or maybe I'm not reading that quite right. Is that the, doesn't look like that would add to 10 to the minus 7. Or maybe 10 to the minus 7, maybe is that the wrong value? Okay. Well, this the last part here is summarizing them, which is going to be a better way than me trying to summarize it by looking. So about 50% of the, oh no, these are just those concentrations. Okay. All right. Well, I actually am confusing myself a little bit because I'm looking at these numbers at 10 to the minus 11 and such, and I would think that if we added all these up on the right column, that should get us to 10 to the minus 7. But maybe I'm misinterpreting something. Okay, so I'm just gonna leave it off there. The book will explain more of that if we need it. But the point is, there's a lot of complexes, and we would need to solve each of them in order to truly understand the system. Okay, so, oops, sorry. The end button is a little too close to the arrow key, and I need to stop using the arrow keys. All right, so the software that this guy used, hypothetically, is Visual Mintech. And this is a free software package. I went ahead and downloaded it this morning. I didn't get far enough to really be able to teach you anything with it, or even decide whether or not we ought to have this as part of kind of that MATLAB computational approach piece of our course. But we may well do that. I'll give you more information on that in the future, if so. But it's a pretty basic program. I think it's just somebody, maybe a couple people have worked on it over the years, who's kind of made it his or her own project to build this and update it and publish it for anybody to use. So a lot of the known constants, things like that, are built into the program, and then essentially what it can do is set up these types of systems to, let's say, run a titration, a modeled or simulated titration with all these rate constants built in. So the type of stuff we did with MATLAB could certainly do that and punch out a number for you, or maybe even a graph. At least an Excel thing that you could then, or a table that you could take to Excel and then graph. So I'm not super familiar yet with all of the different things it can do, but I will say that provide you these links. The website to download it is there. It's free. And then there's some beginner lessons I found where you could watch somebody kind of explain what's going on. So it looks like there's probably a series of lessons there that would take you through. And at a glance, it looked pretty useful. So certainly there are resources out there. And I think each of the books that are modern that we have on the syllabus describe a bit about it and probably provide some further resources. So that's a resource. If I decide we ought to go a little deeper into that, we will go and check that out. Okay, so I wanted to touch on a couple other ligand topics before we move on. A couple of the, I guess, maybe more common, widely used, important cases that are worth considering. One is EDTA. Now this is ethylene diamine tetraacetic acid, almost all one word. So EDTA, it's used pretty commonly. You can see it over here on the right. We could describe this as H4Y, meaning, you know, kind of how we did HA or H2B and so on. We have four protons that could all leave, right? So it's kind of like an acid with 4 protons. And the interesting thing about it from a ligand standpoint is it has 6 sites, so it's hexadentate. So it's a hexadentate ligand, 6 sites that it would be happy to attach to and interact with a metal. And those would be 2 nitrogens and 4 carbons. And I think, actually it's a good question about which carbons. I don't know if it would be these carboxylic carbons or perhaps these branching ones. I kind of doubt it would be these guys. I think they'd have to be a little further from the nitrogens. So I don't think it would be these ones or these ones. I think it would be these 6 sites. It's my instinct. At any rate, that will make a nice chelate because that's going to wrap around some ion. And it's really nice for some metal that wants 6 bonding sites, right? So a metal with a coordination number of 6 would be quite happy to be grabbed by EDTA. Turns out that this works really well with things like calcium and magnesium. So a lot of the 2+, so the divalent metal ions tend to work really well with that. And so with that, we actually use EDTA to measure hardness because hardness is essentially a quantification of the calcium and magnesium. Now, a side note here that we'll get to, I think we'll talk more about this later, but hardness, if we think about our what we learned with the alkalinity and things like that, hardness is kind of related in that if we have a lot of hardness, there's a good chance, so we have a lot of these calcium and magnesium in particular, there's a pretty good chance we also have a fair amount of alkalinity because these are cations that kind of provide that balance of inorganic ions that aren't affecting solution, right? So they could satisfy, like if you added calcium hydroxide, right? There's OH minuses there that would be released. Or on the flip side, you could add, like these would satisfy that. So as we think about the types of ions that could contribute or affect the acid-base system, affect carbonate, we can think of calcium as taking up carbonate to form calcium carbonate, right? So these tend to be involved with that type of stuff. And when we deal with hardness, it'll look pretty similar to our alkalinity type equations. So that'll be pretty familiar. Okay, so coming back to EDTA then, because it binds really well, we can essentially use EDTA to titrate a solution with calcium and magnesium to say at what point do we have a big change in concentration there? How much EDTA does it take until we kind of reach some sort of threshold? So looking at EDTA, with the four protons that can come off, we can actually look at the molecule kind of as Y4 minus. So if we take all four off, that becomes Y4 minus. We could also possibly add hydrogens to it, right? So if we then consider, there might be quite a few forms, right? We have HEDTA, that'll be a 3 minus, H2EDTA, 2 minus, H3 with 1 minus, H4, that's the standard. Then if we add one, it could be H5EDTA plus, H6EDTA 2 plus. And we could get log K values for each of these. We could look at the pKa for each spot, and it's going to be a relatively complicated system. So when we do take a look, here are those different species, so our speciation diagram. If we just look at it, immediately this is going to look a little different than what we've seen with log C versus pH plots. In particular, a lot of these lines, we just have a lot of them, first of all. There's so many lines that are overlapping. And when we have many that are kind of clustered together here, we recognize that they're pretty slopey. And our typical plan of let's draw a straight line from here to here, and then bend it a little between this point and this point, and then go straight again, that's not really going to work. And also, when we have so many overlapping, we're not going to be near enough to some total mark to say that at this pH, this one dominates, right? That's just not going to happen. We're not going to have the same shortcuts that we had been using, at least for some regions. Now, one thing we will notice, there's a segment that turns out to be pretty important where HEDTA 3 minus is dominant, and in that range, we can use some of those assumptions. So just wanted to point this out, and the curving lines, that I did kind of mention the slope change as we previously looked at. We went from a slope of 1 to maybe 2, and there was some transition there. Here it's just slopey, right? There's too much going on, especially in the left side of the graph. So our book says, okay, this figure showing that HY3 minus is predominant at the range between about 6.2 to 11-ish. And the Y4 minus, so EDTA 4 minus, which is actually the complexing ligand, does not become dominant until the pH exceeds about 10.95. So the question is, at what range can we titrate solutions using containing calcium to get a sharp endpoint to out? Meaning, when is it going to show a sharp change in the calcium concentration when we add a small amount of our ligand? So this titration is a little different since we're not adding an acid or base. We are adding this complexing agent because at some point it's going to complex the calcium and kind of take it out of solution in that regard. So that's what we're going to observe. So the standard procedure for measuring water hardness, which is essentially calcium plus magnesium, calls for titrating water samples buffered to 10 using a standard EDTA solution. Okay, so measuring calcium by itself, we actually do that at a higher pH. That'll get rid of all the magnesium. That will also start forming some calcium carbonate, which is a problem because we wanted to measure the calcium, but that's slow enough that we can get rid of the magnesium first and then carry on. So timing of some of those reactions will be important. So if you've ever done any of the colorimetric method stuff, especially on hardness or looking at calcium, the timing of your reactions is kind of dictated by these processes. And These are why we're adding a particular reagent to, okay, put it in this form and then cause that to happen. Okay, so I'll get us an example here so we can see it in action. I think that's always helpful. But the question about at what pH can we do this? Can we use EDTA to complex calcium is going to come from, like if we take a look at when is the actual complexing agent active and to what extent does this guy matter? Well, we can check at a few different pHs, check this titration and see what happens. So that's what this part is doing, and this was, the book said this is something that was created in MinTech. So again, this might be an example of what we can do with it to say, okay, let's try this titration and plot the PC, so the negative log of our concentration of calcium, as a function of adding EDTA. So we've got some concentration that we start with. As soon as we start adding EDTA, it's dropping the concentration. And remember, this is calcium 2+. So the reason it's dropping should be the formation of the EDTA complex. Right, so that's not going to be observed when we are, so what we're saying is that this is not total calcium in solution, this is calcium in the 2+ hydrated form, right? So as we're adding EDTA, we start seeing a small change. So there's some complexation happening, and we might expect that if there is some equilibrium between, like we saw last time, there's going to be some equilibrium between water leaving and EDTA coming onto this system. But for a little while, until we get up to about 10 to the minus 3 moles per liter for this condition, nothing really happens. So, or not a lot happens. A little bit's happening. Now at pH 5, then we have, once we cross that mark, a little bit of a change, but mostly there's not a rapid change as we keep ramping up the EDTA concentration. At pH 7, we get a nice big change as soon as we hit this threshold. And at this threshold, I know I cut off the caption a bit, but this I think relates to how much calcium was in solution in the first place. That's typically why we want to titrate something, is to find out what concentration of this do we have to add so that we know what concentration of that there is, right? Because if we get a 1-to-1, if that's the scenario, if a 1-to-1 concentration titrates everything and it drops significantly, we know, okay, that's how much calcium we have. So that's kind of the plan, is to find out at what point have we added enough to complex it all. And you see the PC negative log of the calcium, if it's dropping to a minus 10 or something, that means the remaining concentration in solution is 10 to the minus 10, right? So if it's, at first we start with a concentration of 10 to the minus 3, right? And so actually that's a way to say 10 to the minus 3 is kind of the key that we're looking for. So that's why we're matching right here. If our calcium starts at 10 to the minus 3, as soon as we start adding some EDTA, we get a little bit of removal. Well, as soon as we add a 1-to-1 ratio, that's when we see a big drop, especially on a log plot like this. This is why it's going to be pretty useful. So at pH 7, it works, but at pH 10, it really works, right? Now, the book goes on to describe that if we really stop and think about it, the precise details of how much of this we're adding per drop, the pH 7 is actually not very practical, because we end up adding, we don't see an enormous change for every drop we add, so it gets a little, like it could kind of work theoretically, but it's going to throw a wrench in the practical application of it. So therefore, pH 10 is really the standard standard method because at that range we've got plenty of the, or I guess enough of the Y4 minus. As soon as we complex with the Y4 minus, the equilibrium will draw some more to Y4 minus from the HY3 minus, right? So we're actually, if we have at least some meaningful fraction of it, we'll still get some of it. Now, if we were down less than pH4, there's like no chance at all. And even just down here, it would be so slow that to transfer into enough Y4 minus that it just wouldn't be practical. So that's why we kind of see that, see what we saw in the pH in this graph. Okay, so I want to take a look, just watch a quick video just to see how this is. And let me, oops. What did I just do? Oh, it's Halloween. Okay. Just make sure my sound is working properly here. Just take me just a moment to get my sound. Okay, how about through that? All right, it should be working, but it's not. Let's try one more thing, and then I'll just play it from my laptop if I have to. Oh, there we go. Okay, good. All right.
Of water hardness. Attention, in this experiment hazardous compounds are used. I don't take any responsibility for damage done to persons or for the determination of water hardness. The water is left to run for a short while. When it has been sitting in the pipe, it is possible for it to contain additional contaminations like heavy metal ions, which can have an influence on the measurement. 3 solutions are needed. A buffer solution with a pH of 11, which is an aqueous solution of ammonia and ammonium chloride, an aqueous solution of sodium EDTA, and a solution of areochrome black tea in ethanol. For the titration, an Erlenmeyer flask with a stir bar is placed on a magnetic stirrer. Over the flask a burette is placed. Before filling the burette, it has to be made sure that the stop cork is closed. Then it can be filled with the EDTA solution. At first, bubbles of air are trapped inside, which is why the burette is filled above the highest marking. To remove them, the stop cork is opened somewhat quickly and the excess solution is collected. Then the level of the solution can be adjusted to the highest marking. The meniscus causes the broad line on the back to taper, making it possible to read the values precisely. Next, a sample of 50 ml is taken from the water that should be measured. Then the indicator is added. It was found out that the amount was way too low, so more should be added. After adding 10 ml of the buffer solution, the sample is ready for the titration. In the first run, the EDTA solution can be added quite fast, then the following samples can be determined precisely. The solution changes its color to blue when the titration is finished. To the end, it is important to wait a few seconds between the additions because the change can take a while. It can take several seconds until the color change takes place. In the first run, 2.6 ml of solution were added. In total, 6 samples were measured and at the end the mean value was calculated. Then, per milliliter of EDTA solution, you get 5.6 degrees German hardness, which leads to a value of 14.45 degrees German hardness. This is quite high, but close to the value of the water utility. Due to the distance to the water source, it is expected that the values tend to vary, as it can be seen here. The unit degrees German hardness is only used in Germany and very old, which is why there are a lot of different units for water hardness. From the scientific perspective, the correct unit would be millimoles per liter, so 14.45 degrees German hardness would be 2.58 millimoles of alkali ions. The concentration C of the earth alkali ions is calculated by first multiplying the volume needed with the concentration of the EDTA solution. The result is the amount of moles of EDTA. 1 mole of EDTA binds to 1 mole of calcium or magnesium ions, so the value of EDTA is the moles of the ions. Dividing the moles by the volume of the sample leads to the concentration of the ions in moles per liter. When the values of the measurement are put in the equation, it can be seen that the value of the concentration and volume of the sample are the same, so the volume of the EDTA solution quickly leads to the concentration of the ions in moles per liter or millimoles per liter. This was the determination of water hardness. I hope you enjoyed. Please rate and comment.
All right. So, always fun to watch some color change, right? And so the color change is kind of what we're looking for because that's showing, that's the complex showing up. So that's going to be, in this case, I believe that's what's happening here is that we have the calcium in solution, the EDTA in solution, whatever buffers, but the EDTA is not enough yet, and so it just looks pink until we have the EDTA calcium complex form, and boom, suddenly that's our big transition. So we're going from that pink color here to blue here with the complex formed. Okay, make sense? All right, so there are some other important ligands around. Cyanide is one that we'll talk about for a moment. Definitely not being exhaustive here, and I just wanted to kind of give you a flavor of what else we could kind of think about and take a look at what's possible with something like Mintech or other software. So cyanide is a strong, I guess the book says a moderately strong ligand for class B metals. So if EDTA is getting calcium and magnesium, I think those are the class A range. we could get something different, something like cyanide for the class B. So cyanide is toxic, you probably have heard. So CN minus, but it's important for a lot of industrial applications. So even something like extracting gold, I believe you can do with cyanide. Again, it has these particular ligand properties, which is probably related to the reason it's toxic. It has some specific activity. So zinc cyanide is one system we could take a look at. And if we look at a plot of the fraction that is of total zinc and look at it compared to, as a function of adding cyanide, we can see that with no cyanide present, almost all of the total zinc in solution is in a zinc hydroxide, so ZnOH2. No charge there. But as soon as we start adding cyanide, our total zinc is dropping, or that form of zinc. But we might also notice that perhaps the total zinc is actually dropping. So we might be precipitating some, or just, let's see. Yeah, I think we're causing some to precipitate immediately. Because if we look at, let's say right here, 0.6 of the solution, oh, maybe not. I was thinking that maybe this total doesn't add to 1 at any of these points. Maybe I'm wrong and just yeah, I'm probably just wrong about that. But so we immediately start forming some zinc cyanide there, and some of these other compounds get a little bit of the ZnOH3 minus. I guess we started with a little bit of that itself. And we can see at different levels of cyanide, we end up with different complexes. Ultimately, with, if we add enough, we're getting mostly the CN4 2 minus. So we can take a look at how much do we need to add to get some outcome. And again, this is going to relate largely, this is all going to be that equilibrium chemistry. And if we add a whole bunch, we probably just end up with primarily the 4 complex zinc. We can also take a look at what happens over different pHs. So we have another plot with the P concentration per pH, by pH, and we can see at what levels are we getting different, at what pHs are we getting different species. And this is a plot from pH 6 to 12, and we see at the higher end, we're starting to get those hydroxides. And so if we might look at going all the way up to pH 14, might spike those and start removing a fair bit of the cyanide complexes, just given the favorability there. So just kind of showing some of the complexity that can be there. Trying to do any of this by hand or in a manual fashion, going to be pretty difficult, right? So, and if we stop and think about the relevance for a given application, or trying to understand how to treat something, how to remove something, how to process something, we can see perhaps it might be really important to find when we have Zn2+ in solution, right? And that would be, there's a lot of factors here that would go into saying, okay, under what conditions does that happen? What happens if the pH gets jumped up by half, by 0.5? In some cases, that could be a big deal. Okay, so that's kind of about it for ligands, and I want to shift gears then to solubility. Like I said, this is going to be relatively straightforward in terms of we've already learned a lot of the pieces to do this stuff. So it's going to be applying multiple angles, tying things together, and then making some nice plots to consider, kind of like what we were just looking at, but perhaps even a little more useful to say, okay, where does this thing precipitate? We'll see that a lot in applications like coagulation flocculation, where we want to add a coagulant, let it dissolve, and then maybe tweak the conditions a little bit so then that we're getting a lot of precipitation. Water softening, where we're manipulating the hardness and causing things to come out of solution, and geochemistry in general in terms of understanding, at what pHs will something dissolve, what kind of conditions, what speciation do we expect under particular conditions, what about in the groundwater when it looks like this, what about when that groundwater is drawn up and discharged to a stream, what then, what are the metals and things going to do. So lots of places where solubility is important, and we can see how a lot of these pieces will have an impact. So a few quick terms here. Saturation, of course, that's a condition when we have a solid phase present and it's existing at equilibrium. So if we add enough table salt to my little bit of water in here, that there's still some salt there, even though I've let it reach equilibrium, I've stirred it well, all of that, we're at saturation, right? That's the definition of saturation. So table salt's a good example, NaCl, of a rather soluble compound in water. But you can imagine if I poured 1 liter of salt into here, there's probably going to be some salt remaining. It's probably not all dissolving, right? So there are cases. Something we often consider as insoluble, kind of a sand, silica, SiO2, can dissolve a tiny bit. So we could have SiO2 with water in equilibrium with SiOH4. So it can dissolve a bit. So we would say the dissolution reaction would be going from the left side of the convention is to write the solid on the left and the dissolved species on the right. So in that sense, the dissolution reaction would be the one heading to the right, and the precipitation would be the one heading to the left. So under some cases, we might describe a system, let's say one that is dilute, perhaps we could call it, where I just added a teaspoon of salt here, and it's all going to dissolve. Then that's kind of a forward reaction, and those conditions are such that it's never going to go to the back reaction, or the conditions are not there for that to happen. So we're going to talk about that. That's kind of the solubility product. Even if the conditions are like really, really unfavorable for something like sand to dissolve, a tiny, tiny bit of it will go in that direction, but we don't really see the same in the reverse, or it's just maybe it kind of is, but it would just dissolve so quickly right back that you would never notice. Whereas for the case, it's a little more noticeable for something that's rather insoluble. Over time, weathering, right? Just rainwater will weather something and eventually dissolve the mineral that feels like it's insoluble, but over many years, it's removing a tiny bit of it and flushing the water away. That kind of thing is a little more noticeable than, in a tiny, tiny point of time, maybe you make a solid and then it just dissolves right away. You never have a way to notice that. Okay, so we have a few common rules for solubility that I found were pretty useful. They're good generalizations. Again, nice bit of content from this website, LibreText, the chemistry articles. So salts containing group 1 elements, that's our first column on the periodic table. So that's lithium, sodium, potassium, cesium, rubidium? I don't remember. Rb+, tend to be soluble, maybe even are soluble. There are a few exceptions to this rule. Salts containing ammonium. So in addition to those, salts containing ammonium ions tend to be soluble. Okay, so that was the first one. The second would be salts containing nitrate, NO3-, tend to be soluble. Next, the salts containing the halides, Cl-, Br-, I-, generally soluble. Some important exceptions. So silver, lead, mercury, all not very soluble as as halide salts. In general, most silver salts are not soluble. So sodium nitrate, sodium, or excuse me, I said sodium, silver nitrate, and this one that might be acetate, are common salts of. Oh, excuse me. Those two are common soluble salts of silver. Almost all others are insoluble. Okay, a few more. Sulfates, generally soluble. A few notable exceptions. Calcium sulfates, not particularly soluble, a little bit. Barium, lead, silver, and strontium, all not so soluble. Most hydroxide salts are only a little bit soluble, so we've talked about those sometimes or seen them show up sometimes, like an aluminum hydroxide. So these tend to be kind of on the edge, so you will tend to have some precipitation, even if some amount of it might exist in solution. So hydroxide salts of group 2 elements, so calcium, strontium, barium, are slightly soluble. Transition metals tend to be insoluble, so that's the iron, aluminum, cobalt. Most sulfides, and by the way, I'm saying are or are not soluble. Again, these are generalizations, right? They're going to have some portion that, some fraction that will dissolve, but generally, as a rule of thumb, not so soluble, right? Okay. Most sulfides of transition metals are highly insoluble. So cadmium sulfide, iron, zinc, silver. In addition to that, arsenic, antimony, bismuth, lead sulfides are not soluble. Carbonates often are not. So if we get calcium carbonate, strontium, barium, iron, and lead tend to not be so soluble. Chromates often are not. Phosphates often are not. Fluorides often are not soluble. Okay, so lots of generalizations there. And one thing we noticed there that the fluoride was kind of excluded from the halides, right? So the salts containing chloride, bromide, or iodide are generally soluble, whereas a lot of those with the fluoride are not, even though they're all halides. Fluoride is just such a smaller atom, and it's the most electronegative. Comparing that to chloride, which is a much bigger atom, I think that's a big difference driving whether or not it's going to dissolve. The larger the atom, essentially it's spreading out the distance of that charge. So if you have a really compact -1 charge versus a balloon -1 charge, it's going to affect the way the atoms are interacting, right? And their the strength of the bonds and things like that. Okay, so those are some generalizations we could take a look at. Gives us some idea, maybe some gut impression of, you hear about a bromide salt in the lab or something, you might think to yourself, oh, okay, that's probably soluble, right? We could study that if we wanted to, but just kind of putting that out there as some typical stuff. Okay, I mentioned, but the same thermodynamic principles, finding a delta G, Gibbs free energy, finding a K value, it's the same as the stuff we've done for acid base and all that. In this scenario, when we're doing solubility, we have an equilibrium constant, and we'll call that one a solubility product. And the reason we term it that way has to do with the way we set up a given K, right? So K, typically we say is the products over the reactants. And of course, we are taking the product of their activities and all that. But essentially, if we always set up our reactant as the solid, that goes to 1 because it's a pure substance. So we're going to take any solid or pure liquid to 1 when we're talking about the activity. The reason for that is if we have a solid and we still have the solid in solution when we're at equilibrium, then essentially removing some of the solid doesn't change its effective concentration. It just becomes unity. There's no real effect that has. So this becomes the products, I'm just going to write products, or short, over 1, because that's the solid. So when we say the solubility product, then it's kind of just K is equal to the product of the products, the products multiplied by each other, right? So in that sense, the K, the solubility product, I'll write S, and it's often convention to put a 0 there, for this calcium sulfate is going to simply be, if we do it proper with the activity of the calcium times the activity of the sulfate. Okay, so then our solubility product is the product of the products. It's just the K is equal to that. Okay, we can take a look at the same, for this system, we can take a look at the same Gibbs free energy for the reaction as the Gibbs free energy of the formation for the products minus the reactants. We could continue and say the delta G naught for the standard Gibbs free energy for that reaction would also be equal to negative RT ln K, where that K is that solubility product. And I already mentioned this part, right? So we could, for this case, we could then go look up some values, find the delta G formation for calcium sulfate. So we are including the delta G's for the solid, because we still have to do that. So that minus the delta G formation for Ca2+ minus the sulfate. Put all those numbers into kilojoules per mole and solve for the K, right? So we could do the same thing we've done earlier in the class. So we could get that, find a solubility product in that manner. There's another concept that's pretty useful, and that's the ion activity product. So when we're dealing with something like a salt or something that may or may not be dissolved, dealing with something with a condition where we're potentially precipitating something, there's a decent chance we're at a fairly high concentration. So maybe we do need to use ionic strength or some other way to estimate activity. So that ion activity product would simply be, making sure we're keeping the activity of those two species, or however many species, right? So for the case example, the ion activity product is K. But we can compare a given condition in the water that is the ion activity product to a known K, right? So the distinction here is the IAP is not necessarily a condition at equilibrium. Okay, so this is checking a condition to see and compare it with our equilibrium constant to see what's going to happen. Okay, so if the IAP is less than our solubility product, we're not going to have any solid. Okay, so we can basically tell, we can use the solubility product as a reference to IAP to see, are we going to be precipitating things? Are we not? Where are we compared to that? So it's kind of an elaborate way to describe what may be obvious if we stop and think about it. But it's called the ion activity product, IAP. So if IAP is equal to the solubility product, we're about ready to start precipitating something. It's like the next molecule that we add is going to cause some precipitation. If our IAP is greater than our solubility product, we expect that we have precipitation occurring, which will then decrease the concentration of those ions until we get to the point where we are at equilibrium. Okay, So we could temporarily supersaturate this condition or the solution, and we will be getting some formation there. Okay, there's a good example, kind of a fun one. I'm going to pull up here to watch the solubility of lead iodide. Our book has some instructions to try this in class, but I'm wasn't about to.
Lead salts are toxic. Do not recreate this experiment. Welcome back everyone. For today's experiment, 3.2 grams of lead 2 acetate trihydrate and 2.9 grams of potassium iodide are needed. We started off by weighing out the potassium iodide. Potassium iodide is this white salt, which we then dissolved in approximately 50 milliliters of distilled water. On a piece of paper, we weighed out the lead 2 acetate trihydrate. Lead nitrate could also be used. This lead acetate was made in a test run without using any exotic chemicals, not even hydrogen peroxide or lead 2 oxide. I'm going to repeat this. If you don't want to miss out on this high-yielding preparation of this lead salt, make sure to subscribe to my channel. The lead acetate was dissolved in distilled water. Judging from the cloudiness of the solution, my distilled water likely contained some carbon dioxide. Formed carbonic acid reacts with the lead acetate to form insoluble lead carbonate. Small amount of acetic acid was added to make the solution clear up again. Time for some action. Let's combine both of the solutions. Upon contact, yellow precipitate immediately falls out. This led to iodide. On the top, you can see the reaction that was taking place. Now that we have made this precipitate, it's time to dissolve it again. We placed the flask into heating mantle, which we then turned on. Next time I'll use small amounts of reagents because this was way too much. Some of the lead iodide didn't want to dissolve and sank to the bottom, even if you can't see it here. 2 hours later, lead iodide finally started to crash out again. We got this effect, which looked like golden rain. Lead 2 iodide has a poor solubility in water. At 100 degrees Celsius, 1 liter of water approximately dissolves 4 grams of lead 2 iodide. In comparison to that, 1 liter of water at 20 degrees Celsius just dissolves 0.7 grams. Enjoy the next minute of uninterrupted spectator time.
It actually does look really good. Skip a little bit mesmerizing. So basically what they've done is as soon as you saw them add the lead compound or immediately precipitating that condition, you could do a similar titration thing to adjust the condition so that the lead crashes out in that manner like immediately. And then what he did was he heated it up to re-dissolve it and let it just precipitate again after he pulls it off the heat. And so what he was saying about there was still some left, he heated it to the point where it should mostly all dissolve, but it didn't quite all dissolve, re-dissolved, cooled it off, and then 2 hours later, just
By the next day, all of it sunk to the bottom. I wanted to keep the lead 2 iodide for my compound collection. To obtain it, we first decanted off most of the solution into my heavy metal waste canister. A vacuum filtration was carried out and the flask was afterwards swirled a few times using distilled water. In the end, we were left with this dry, gold-like looking solid. To dry it completely, it was left in a vacuum chamber over anhydrous calcium chloride for a few hours. We were left with 3.5 grams of this fake gold. This corresponds to yields of approximately 90%. Under the microscope, the lead 2 iodide looks like this. It's really shiny like gold. And there you go, we successfully made lead 2 iodide. Besides that, you also saw an amazing experiment. The ampule was labeled and put aside. It really looks like gold. If you liked today's video, make sure to drop me one of these and consider.
Right. nice example there of solubility. Another thing we can start taking a look at is, well, at what condition do we find the that solid? And if we just simply plot calcium concentration versus sulfate concentration, where we were talking about the calcium sulfate, at some range, we will always have the IAP, that ion activity product, below our solubility product, meaning that was the condition where we were not having any precipitates, right? So we said if IAP is less than, we have no solid present. So down here, this would be no solids. And above would be, we have the solid formation, right? The line itself would be where so if we take that line, that's the line where IAP is equal to the solubility product. Let's do this. Okay. So we can make a graph like that. In this case, that's a relatively simple one. If we stop and think about the fact that our activity might actually start changing at some point, the more we have, it might become a little more complicated, and we probably ought to make some adjustment for that, which might become a little complicated, but a computer program certainly could do that. Or as a kind of a crude or rough concept here, we could just simply ignore activity and make that plot to give us an idea of what to expect. And if we look, these values here, 10 to the minus 2, let's say kind of in the middle here, 10 to the minus 2 to 10 to the minus 2 or 3-ish. So with a reasonable amount of them, we'll start getting a solid. So if you're trying to dissolve calcium sulfate into some water, maybe for some experiment, you can't dissolve a ton of it, right? At some point you'll hit that IAP and then nothing else is going to dissolve. We talked last time a little bit about Le Chatelier's principle for helping things to dissolve. Well, there's another concept that we would find important here, especially looking at this graph, is what's called the common ion effect. We can actually prevent things from dissolving if we have some source of extra calcium or sulfate in this situation, right? So if you were in a lab trying to dissolve some calcium sulfate, let's say to get some calcium, but you're doing this in a solution that already had some other form of sulfate in there, then you're more limited because you already have a whole bunch of, what did I say, a whole bunch of sulfate already. So if you've already pushed this to one direction, then you are more limited to the amount of calcium you can get in the solution before you get some dissolution, right? So you can, this is one of those reasons why we can end up with a lot of interferences that we might not have expected. It's like, oh, this method can work. Does it work for fresh water? Does it also work for seawater? That's no guarantee, because things like this could cause precipitation issues when you thought you could measure something normally and then suddenly all this junk is in the way, right? So we need to check our hydroxylamine method for brackish and seawater for this type of reason. Because I know we have some trouble with how much stuff dissolves anyway if we were to push those reagents further. Okay, so we can take a look at an example here, and I think this will be the last piece for today. So we have an example that says when we take stannous tin fluoride, so tin fluoride, SnF2, it's added to pure water, the solubility is 0.012 grams per 100 milliliters. Using only that information, determine the solubility product for SnF2, and then B, consider, I'm just going to add in a little how you would go about determining the solubility of SnF2 in a solution that originally contains 0.8 moles per liter of sodium fluoride. So that's the common ion effect. So take a couple minutes I'll give you a couple minutes to get part A, and then we'll look at, see if you can get part A, and then think about part B, and then we'll take a look together. Sorry, I should have looked it up for you, but you'd need to look up the atomic weights for zinc and fluoride. Tin. looks like some of you are still giving it some thought. Probably pick up here next time. First step, we'll just say real quick, we would need to convert from mass to moles. Now that I gave you that, you could do that. We get concentrations of each of the F minus and the zinc 2 plus, excuse me, the tin 2 plus, SN 2 plus. Then from there, we could calculate that solubility product, right? Given that we found the solubility condition, we could find the concentrations, we can compute that to get a K, the solubility product, 1.8 times 10 to the minus 9. We probably also want to write up the equation, the dissolution, the equation SnF2 would be in equilibrium with SN2 plus 2F minus. So that means we need the exponent on that when we do the concentration of F minus to the second power. So we'll resume here next time. And have a happy Halloween.